So when Chris and I first talked about this presentation, I knew that I wanted to talk something about 3D graphics. But since SceneKit isn't available on iOS, we thought at first that maybe I can say something about GLKit. Then I visited the Alt Tech Talks here in Berlin, and I saw this tweet in response to a presentation there about fast shader development. And I thought that is a really good idea, actually. So that's what I'm going to talk about. And as Max said, there's no short introduction to OpenGL either, but I'm going to attempt one. And it's going to be a mixture of concepts and practice, and there's going to be a lot of new terminology. Sorry, the screen keeps flashing. There's going to be a lot of new terminology, and but I still think it's better to try and use the correct terminology, because if you want to find more information about stuff afterwards, then you know what to search for. So at first glance, OpenGL looks a little bit like core graphics. You have a graphics context or a rendering context that you change the state of, and it maintains that state. And you send commands to it that are interpreted and executed using a C API. But of course, the two of them aren't really similar. One big difference is that the OpenGL context is not the render destination. So you're not rendering into the context, because the OpenGL context contains all of the OpenGL state. It contains, for example, references to what shaders are being used, or what is the current frame buffer, which is the render destination. Another huge difference is that the OpenGL context persists between frames, which the core graphics context doesn't. So that analogy doesn't hold up very well. But it can feel nice to start out with something that feels familiar, and then take it from there. I mentioned buffers and frame buffers. And a buffer is really just memory that OpenGL and the GPU can manage. And the frame buffer is a collection of these buffers that you can render into, so they are the render destination. For example, you have the front and back color buffers that are used to display pixels on the screen. You have the depth buffer that is used to depth test, so that you don't render something that would appear behind something else. You can also have a stencil buffer, which is used to mask out things. And that works similar to mask layer on CA Layer, if you ever use that. Before you can render anything in OpenGL, there's a bit of work that needs to be done. You need to create this render context, and you need to make it the current context, so that that is the one you're working with right now. Because you can have multiple, but in many cases you only have one. Then you need to create these frame buffers and the render buffers for color and depth and all of that. And you need to make the frame buffer the current render destination. And you need to configure the viewport, which is the shape of the viewable region. And after you've done all that work, then you can render. And at this point, many of you, including me, are reminded of why you're not really using OpenGL, because it's a big hassle. But I have some good news for you, and that is, if you're using GLKit, which I really think that you should, then all of those things will be managed for you. And one thing that is even more impressive is that GLKit fits OpenGL into the view controller semantics that we as iOS developers are very used to. Because OpenGL is very generic, and it doesn't know anything about iOS, but GLKit does. And GLKit also does a lot of things for us. It manages the interface orientation so that your iOS app, your OpenGL app, behaves like an iOS app should. You won't get a flipped screen when the user uses their volume toggle and get this HUD over your application. It's going to work like an iOS app should. GLKit will also pause the animation timer and dispose of the frame buffers when you go to the background. Because if you try to access the GPU while in the background, then your app will be terminated. Of course, it only manages the buffers or the resources that it creates itself. If you create your own resources, then you need to manage those. GLKit also makes it so that the view will render its content on demand. And this is signaled by calling setNeedsDisplay on the view. And the view will then pass the rendered content onto the composition part of core animation, which caches it, so that if the content hasn't changed for the next frame, then you can simply reuse the cached content. And for a regular UI view, when drawRect is called on the view, the core graphics context is already set up so that inside of the drawRect implementation, you only need to care about the actual core graphics drawing commands. And just the same way, when drawRect is called on your GLKit view, the context is already made current, and the frame buffers and all the render buffers, they're already created and bound, and everything is configured so that inside of the drawRect implementation, you only need to care about the actual OpenGL drawing commands. And this is very nice, because this feels familiar to us once again. So what are we actually rendering inside of drawRect? Well, OpenGL renders triangles, lots and lots of triangles, because a triangle is the smallest polygon that forms a surface. If you have just a single point, then that is just a point. 2 points together can be used to form a line, and 3 points form a triangle which has a surface area. Of course, 4 points can also form a surface, but that same surface can just as well be described by 2 triangles. And that is the beauty of triangles. So everything you render in OpenGL is made out of triangles. And those triangles, in turn, they're defined as a series of points. And all of these points are defined relative to the origin of that model object. In this case, the origin is in the center of the base. This is called the local space, or the local coordinate space, if you feel like being more explicit. And the benefits of having local space is that it is independent of the rest of the world. So each 3D model can be defined, modeled, and created, and saved individually. To know which points to form triangles in between, all the points are giving an index. And 3 indexes is enough information to define a triangle. And then to define triangles between all of the points to form the full surface, then you just need a long list of indexes. The order of these indexes also matter. By default, if the indexes are defined in a counterclockwise order, that means that the surface will be facing towards you. This matters because by default, triangles that are facing away from you won't be rendered. And the reason they aren't rendered is because in a solid object like this one, there would always be some triangle that is facing towards you in front of that triangle. So even if it were rendered, it would never be visible. If you're loading a 3D model from a file like this one, then you don't really need to care about any of this because the 3D artist has already gone through the work of correctly modeling the 3D object. But if you were to generate your own geometry objects in code, then you just need to be aware of this. So to render a 3D model like this one, we send the point data and the index data to OpenGL. But before they are actually formed triangles from these data, all of the points are translated into their correct positions on the screen. Conceptually, this happens in 3 steps. The model object has a position and a rotation and a scale somewhere in the 3D world. So all of the points that make up the 3D model are transformed from what is called local space, as I mentioned before, into world space. Also conceptually, the world is seen through a camera. and it's sometimes also called an eye. And as the world sees it, the camera moves around and rotates, but as the camera sees it, the world moves and rotates around the camera. So for us to observe the world through the camera, we transform all the points into what is called view space. Additionally, in real world, objects that are further away from you will appear smaller. And this is called perspective. And to create the same effect in 3D graphics, we project all the points onto a plane. But this in itself won't really create the effect, but it will make preparations for the effect to happen later on. And it does that by calculating a fourth value for each point, called W. You know, X, Y, Z, W. It's just the next letter. It transforms them into what is called clip space, because at this point, objects that are outside of the viewable area, they are removed, because they wouldn't be visible. Later on, OpenGL will use this W value in what is called perspective division, where X, Y, and Z is divided by W. And when that happens, the world and everything inside of it is transformed into what is called normalized device space. And when that happens, objects that are further away actually become smaller the way we would perceive them on screen. You may have guessed, or perhaps you already knew about it, that these three steps are described by transformation matrices. And one of the nicer things about matrices is that they can be multiplied with each other in a specific order to create a new matrix that does the same thing as the other ones did together. So for us, this means that the full transformation from local space into clip space can be defined by a single transformation matrix called the model view projection matrix for these three steps. As some of you know, I could stand up here all day just talking about transformation matrices, but I'm not going to do that. But if these things aren't clear to you, then for now you're just going to have to take my word for it, and please ask me about it afterwards, because I love talking about this stuff. All of this data processing of transforming the vertices from local space into clip space happens in a programmable stage in the OpenGL render pipeline called the vertex shader. And a vertex is just the name of a corner in a polygon. And that's what these points are to our triangles. They're the corners, so they are the positions of the vertices. Shaders in OpenGL are written in a language called GLSL, which stands for OpenGL Shading Language. And it looks pretty much like C, with some additional data types for vectors and matrices, because we use them a lot. And it has standard operations, standard functions and operators to work with vectors and matrices, as you would expect from linear algebra. The vertex shader takes two types of input that we pass to OpenGL. Attributes, which vary for each vertex, like, for example, the position of the vertex. And uniforms, which are the same for each vertex, like, for example, the model view projection. I don't expect you to be able to write OpenGL by just saying this, but you should be able to more or less read it. And this is actually a full vertex shader that translates all the points from local space into clip space. It does so by taking the model view projection matrix and the position as input. And it multiplies the two of them, which transforms the points, and assigns it to GL position, which is the output of the vertex shader. And this gets executed for every vertex, so for every point in the 3D model. After that, all of the transformed points are assembled into these triangles using the index data that we had from before. And these triangles are rasterized into pixel-sized samples, which are called fragments. And each fragment has its color calculated in another programmable stage, which is called the Fragment Shader, that executes for every fragment. So as the smallest possible example of a fragment shader that I could show you, this is one that assigns the same color for each vertex, for each fragment. And it does so by assigning red, green, and blue an alpha value to GL frag color, which is the output of the fragment shader, the color of that fragment. So these two shaders together, with the 3D model from before, they would render like this. And it's not really the most exciting thing that you've ever seen. To be able to do a more advanced rendering than this, then we need more information from the 3D model. And to know how much light conceptually hits a surface, because there are no real lights in OpenGL, just a bunch of calculations. To know how much light hits a surface, which in turn describes how illuminated that surface is, we need to know in exactly what direction the surface is pointing. And this is called the surface normal. And it's a direction, which means that it's a vector, and it has 3 components, x, y, and z. These are the surface normals for the 3D model I'm showing. The surface normals are also defined in local space. So when we are transforming our model into view space, we also need to transform the normals into view space. And at first you may think that we should multiply them with a model view projection to get them into view space, just as we did with the positions. But that won't do exactly what we want it to do. It turns out that what we actually want to do is to multiply them with what is called the normal transform, and that is defined as the inverse transpose of the model view projection. And if you're uncertain about your linear algebra, then once again, you're just going to have to take my word for it. And be aware, or take caution, and no, take calm, that you don't need to calculate these things yourself. You only need to be aware that these are the calculations you need to make. So if we leverage this normal data that the 3D model has, that the artist has put into it, then we can shade each fragment individually based on its angle towards the light source. And that can create a much more realistic shading than what we had before. We can also use images to add more detail to the 3D model without having to add more triangles to it to make it more complex. And conceptually, there's a problem here that we need to overcome. And that is, how do we know what part of a 2-dimensional image to display on the surface? Once again, the 3D artist has already done this work for us, so it would just work. There's no calculations that we need to do, but it is nice to understand conceptually how this is happening. So this 3D model that I'm using right here, it's mirrored, so I'm only going to show half of it. But conceptually, it's a lot like peeling an orange and then laying down the pieces on a flat surface. So you may need to break up the 3D model into smaller pieces to be able to unfold them. And that's what you do. You unfold them, flatten them out, and lay them on a 2D surface, which is the image. Then for each vertex, you store the 2D coordinate, so that when you're using a real image later on, then you know what parts of the image to display on each triangle. And with this data being read for each vertex from the geometry data on file, then we can display an image on top of our surface. But one extremely powerful thing about images, and perhaps the most fun thing about 3D graphics, is that image data can be used for so much more than simply color. For example, a red, green, and blue value can be used and interpreted as the x, y, and z surface normal at that point. And that can be used to fake additional detail on the surface that isn't really there. You can also use textures, which is the images we display on the 3D model, to have pre-calculated lighting effects, such as local ambient occlusion, that are too expensive to do. And that can create a more realistic shading on the object, especially under the shin, where the head occludes the shin. So assuming that we have our shaders written to do this, because I won't have time to go through that, and we have already loaded the 3D model, how do we actually send it to OpenGL so that we can render it? Part of that is setup code that we only need to do once, and part of it is the actual drawing, the code that we will put inside of DrawRect. For the shader setup, we create 2 shaders, and we get back 2 numbers to reference them by. And then we pass the text, the code, to these shaders and compile them, and keep track of these numbers. Then we create what is called a shader program, which gives us back another number to reference these by. You'll see that OpenGL does things a little bit differently than Core Graphic. Core Graphics likes to pass structs around, but OpenGL likes to reference things by numbers. So we create a shader program, and we attach the vertex shader and the fragment shader, which are referenced by those 2 numbers, to it. Inside of our shader code, we have these attribute variables, which we are referencing by names, such as position, normal, and texture coordinate. And to easily be able to reference those attributes in our code, we bind those to a number that we decide. But in this case, I'm using numbers that are defined in GLKit, because those variables have the name, attribute, and position, attribute and normal. So they are very descriptive. We do these for all the attributes, and then we link the program, just as you would compile and link a program, except that this happens in runtime. When we have done this, we read the locations of all the uniforms that, because we're going to pass data into those later on. So we store those locations also for later use. For our geometry data, we ask OpenGL to create a buffer, and once again, it gives us back a number to reference that buffer by. We then bind it to make it the current buffer, the one that we are working with right now. And we allocate memory in it and send our data to it. But at this point, the data is just a bunch of bytes, because OpenGL has no idea what to do with it. And we do the same thing with our index data. We allocate a buffer for it. We bind that as the current element buffer, and we allocate memory and send our data to it as just a bunch of bytes. So this is the setup part. And what we have from here is that we have passed our data to OpenGL, and we have a bunch of numbers to reference our shaders, our attributes, our uniforms, and our geometry and index data by. For the actual drawing code, we start off by clearing out the color buffer and the depth buffer so that we have a clean slate to work with for our own rendering. And then we tell OpenGL that our shader program is the one that we want to use for all the upcoming drawing commands. Then it's time for us to calculate the matrices that we're going to pass to the shaders. And GLKit helps us with this as well. It can create the projection transform for us. And in this example, I have decided that the model view matrix corresponds to moving the model back a few steps and then rotating it to the side. So I'm just making those calculations myself. And as I explained before, the normal transform is the inverse and transpose of the model view matrix, and GLKit can calculate that for us. And the model view projection is the model view and projection matrices multiplied. So when we have calculated those, we pass those to their uniform locations, referenced by the 2 values that we stored from before. At this point, we are almost there, almost ready to render. But we need to make sense of our vertex data that until this point is just a bunch of bytes. And it's constructed like this, with the positions and normals and texture coordinates all in the same buffer. And this is called an interleaved data, sometimes also called an array of structs. And we do it this way because it is more efficient, because the data for one vertex is in one place. So it gives us a performance boost if we do this, and it's not that much more complex to set up. So we need to tell OpenGL where to find these position, the normal, and the texture coordinates in the geometry buffer that we created before. So to work with it, we bind the geometry buffer so that it is the one we're working with right now, and we enable all these attributes so that they will be used for the upcoming drawing commands. And then we explain to OpenGL where the position, normal, and texture coordinate attributes are found in the buffer. And the stride in this example is the step size from one piece of vertex data to the next piece of vertex data to the data after that, and so on. So that's how far you should go to get to the next piece of data. The offset is within that piece of vertex data, how far should you go to get to the position, normal, and texture coordinates. So we're telling OpenGL that the position starts at the offset of 0, and each position is 3 floats. The normal starts just after the position, because that's how our data is structured, and it's also 3 floats. And the texture coordinate starts after the normal, and that is just 2 floats. So the very, very last thing that we do is it's time for us to draw everything. So we bind the index buffer as the element buffer, and we tell OpenGL to draw all of the elements that are defined in that index buffer as triangles, and that each index is an unsigned int. That's the explanation we give of the index buffer, so that OpenGL can make sense of it. And if we do this, then the 3D model that we have created will render to the screen with the shaders that we have written and the textures that we have. And it's quite a lot of code, actually. But it has a nice structure to it. And once you get used to referencing things by number, then it's really not all that bad. So if at this point OpenGL feels a little bit less scary to you than it did about 30 minutes ago, then I have 3 quick tips for you. All of the documentation for the OpenGL functions, they can be found in man pages. You don't get to them by option clicking in Xcode. But they're really good. And man pages aren't that scary. Oops. Secondly, if you get into OpenGL, then you should really take some time and learn the OpenGL ES debugger. It is integrated into Xcode, and it is really good. But the debugger is probably a 30-minute talk in itself, so I'm just going to mention that it exists and let you figure out how it works for yourself. Also, when you get everything working, your program renders everything as you want it to do, then you can use the OpenGL ES Analyzer instrument. And it will help you tune the performance of your code, and it can point out ways that you can improve it by, for example, telling you that you should use vertex buffer objects or interleave data like we did in this example, both of them. And much smaller things like you have redundant state changes that you can get rid of. And it rates these by severity so that you know what things to target first. That is also a 30-minute talk in itself, so I only have time to mention that it exists and that it's a good tool. That is actually all I have to say about OpenGL. And even though I think this was a pretty intense talk, I've only just scratched the surface, actually. There's a lot to OpenGL that I just didn't have time to talk about.